Hello guys, today we're going to discuss about the basic subsurface flow in steady-state conditions. First, we're going to talk about Darcy's law. In 1856, a French hydraulic engineer named Henry Darcy published an equation for flow through a porous medium that today bears his name. Darcy's law refers to the amount of fluid that flows through a permeable medium or body. According to this law, the flow of fluid between 2 points is directly related to the difference between vertical elevations at different points in the medium and indirectly related to the distance between those points in the medium. Henry Darcy first tested this by passing water through a column filled with sand. Water flowed through the sand beds as it passed. Based on the result of these experiments, Darcy's law equation was formulated. It is also states that It also states that the flow of fluid between 2 points is directly related to pressure differences, distances, and interconnectedness of flows in sediments. Darcy's law describes the relationship between the instantaneous rate of discharge through a porous medium and pressure drop at a distance. Darcy's law equation is expressed as follows. Q, which is the rate of water flow, is equal to the negative of K, which is the hydraulic conductivity, multiplied by A, which is the column cross-section area, dH over dL, which indicates a hydraulic gradient. We have here the Darcy's law diagram. Darcy's law is critical when it comes to determining the possibility of flow from a hydraulically fractured to a freshwater zone because it creates a condition where the fluid flow from one zone to the other, which determines whether hydraulic fluids can reach a freshwater zone or not. These are the limitations of Darcy's law. Darcy's law can be applied to many situations but does not correspond to these following assumptions: unsaturated and saturated flow, flow in fractured rocks and granular media, transient flow and steady-state flow in aquithards and aquifers, flow in homogeneous and heterogeneous systems. So where is Darcy's law applied? Darcy's law equation is primarily used in hydrogeology, and it forms the basis of many hydrogeological equations. It is the formula that states how water flows through a porous or permeable substance. By applying Darcy's law formula, groundwater quantities can also be determined. In aquifers under the ground, Darcy's law is applied to study the groundwater movement. And equations for topographic groundwater flow in saturated, confined, and unconfined aquifers are derived from Darcy's law. So what are aquifers? Aquifers refers to the underground layer of permeable rock or unconsolidated materials such as gravel, sand, or silt. It is a body of saturated rock through which water can easily flow. There are two kinds of aquifers. First is confined aquifers. Confined aquifers are where thick deposits overlay the aquifer and confine it from the earth's surface or other rocks. A confined aquifer can be characterized by the quantity of groundwater flow per unit area. Here we have a sample problem using Darcy's law in a confined aquifer. A channel runs almost parallel to the river and they are 2,000 feet apart. The water level in the river is at an elevation at 120 feet and 110 feet in the channel. A previous formation averaging 30 feet and with K of 0.25 feet per hour joins them. Determine the rate of seepage and flow from the river to the channel. Here we have the solution. The second type of aquifers is the unconfined aquifers. Unconfined aquifers are where the rock is directly open at the surface of the ground and groundwater is directly discharged, for example by rainfall or snowmelt. Groundwater discharge per unit of aquifer width can be determined by Darcy's law when the aquifer is unconfined.
Groundwater flow in confined aquifer. Confined aquifers. These are permeable rock units that are usually deeper under the ground than unconfined aquifers. They are overlain by relatively impermeable rock or clay that limits groundwater movement into or out of the confined aquifers. These are made up of rock materials with a property of low permeability rate, means these clay or rock materials limit fluid to pass through. Confined aquifer is located lower than unconfined aquifers, as you can see in the figure, and where water was also stocked. The rock materials that cover confined aquifers, both up and down, is called shale, also presented in the figure shown. Because of this shale, water on confined aquifer tends to rise up inside a borehole drilled because of underground pressure experienced by the water. Groundwater is a confined aquifer under pressure and will rise up inside a borehole drilled into the aquifer. As I said earlier, the level to which the water rises is called the potentiometric surface. An artesian flow is where water flows out of the borehole and under natural pressure. Confined aquifers may be replenished or recharged by rain or stream water, infiltrating the rock at some considerable distance away from the confined aquifer. Groundwater in these aquifers can sometimes be thousands of years old. So, as earlier I said that it was stuck in the underground. Benefits of confined aquifers. One of the known benefits of an aquifer is a well. Artesian well or well tapping groundwater that is under pressure. In some artesian wells, the pressure is high enough that a pump isn't needed to bring water to the surface. These wells are known as flowing artesian wells. These wells is connected to the confined aquifers. In the figure it was shown. Water in this section was properly filtered, which make it safe water for portable use. In the figure, it is connected to confined aquifer, and because of underground pressure, it automatically rise up even though without the use of pump.
Good day everyone, I am Camille Soro and I will discuss the groundwater flow in unconfined aquifer. Let me first define what is unconfined aquifer. If there is homogeneous porous formation extending from the ground surface up to an impervious bed underneath, rainwater percolating down in the soil saturates the formation and builds up the groundwater table. So this aquifer under water table conditions is called an unconfined aquifer, or what we call water table aquifer, and well drilled into this aquifer is called water table well. So let me show you the illustration showing where unconfined aquifer is located. So as you can see, groundwater is in direct contact with the atmosphere through open pore spaces of the overlying soil or rock. So dyan sa sinasabing pore spaces, dyan pumapasok yung mga rain or yung mga stream water na pwedeng maging part ng groundwater. So, and meron din tayong natawag na upper groundwater surface. So, yung upper groundwater surface na yon is an unconfined aquifer is called the water table. Water table, yung tawag. And, yung water table na yan, meron yung depth. Depth ng water table. So, it varies according to factors such as topography, geology, season and tidal effects, and the quantities of water being pumped from the aquifer. Always put on your mind that unconfined aquifers are usually recharged by rain or stream water infiltrating through the overlying soil. So, it is very opposite to the confined aquifer. This formula is used to find change in groundwater storage. It is equal to area of the aquifer times fluctuation in groundwater table times storage coefficient or specific yield for unconfined aquifer. So, kadalasan tong ginagamit and kung ano lang yung hinahanap, just manipulate the formula. For much better understanding, here is an example for groundwater flow in a confined aquifer. I will first read the problem. In a certain alluvial basin of 100 square kilometer, 90 cubic millimeter of groundwater was pumped in a year, and the groundwater table dropped by about 5 meter during the year. Assuming no replenishment, estimate the specific yield of the aquifer, and if the specific retention is 12%, what is the porosity of the soil? So in this problem, there are two requirements, which is the specific yield and the porosity. Specific yield of the aquifer and the porosity of the soil. Kanina meron tayong formula na nabanggit and meron dong specific yield, and it is for unconfined aquifer. So just substitute all the given in the formula and a specific yield will be left. We have 90 cubic millimeter as change in groundwater storage, 100 square kilometer for area, and 5 meter for the fluctuation in the groundwater table. By substituting all the said given to the formula, you can now solve for specific yield. It is 0.18. Now let's move. By the way, specific yield for unconfined aquifer is unitless. That's why the answer for this is only 0.18. Let's move to the porosity. The formula for this is N stands for porosity is equals to SY plus SR, wherein SY is your specific yield, which is 0.18, and SR is the retention. Now solve for the porosity by substituting the SY is equals to 0.18 and SR is equals to 12% or 0.12 meter to the 0.12 to the formula. The final answer would be 0.30 or 30%.
Radial groundwater flow. So, meron tayong dalawang klase ng radial groundwater flow in an aquifer. Yun ay ang confined and unconfined. So, pag sinabi natin radial, meron itong circular area. Pareho ng mga wells and pipes. So, yung tubig, it flows in a radial area. Yun nga, yung well, kung napapansin yung well, para siyang cylinder, and yung mga pipes. Steady radial flow to a well. So, when soil is pumped, water is removed from the aquifer surrounding the well, and water table or piezometric surface, depending on the type of aquifer, is lowered. So, ito yung tinatawag natin na drawdown. So, ano nga ba yung drawdown? Yung drawdown, ito yung height ng yung water surface sa well. Pag nag-start ka na mag-pump, yung height na yun, bumababa yun. Yung water level na yun, bumababa yun pag nag-start ka na mag-pump ng tubig. So, yung pagbaba na yun, yun yung tawag na drawdown. So, in a confined aquifer, yung hinahanap natin dito ay yung transmissivity. So, ano ba itong transmissivity? Transmissivity describes the ability of the aquifer to transmit groundwater through its entire saturated thickness. It is also measured as the rate at which groundwater can flow through an aquifer section of unit with under a unit hydraulic gradient. So, transmissivity can be determined from a pumping test using the levels of drawdown over time pump. So, in this slide, we have the equation of transmissivity, where T, transmissivity, equals to Q over 2 pi times H sub 2 minus H sub 1 ln R2 over R1. So, yung Q natin dito, ito yung rate ng water flow. 2 pi, or itong H sub 2 natin, H sub 2 minus H sub 1, ito yung drawdown. Or, yung, ito yung height na, initial height, yung height ng well nang hindi pa pinapump, minus yung height niya nung na-pump na siya. So, ito yung distance ng pagbaba ng tubig or yung drawdown. ln R2 over R1. Ito naman yung R2 over R1. This is the static pressure head or yung distance ng monitoring wells. So, makita natin sa next slide. I'll give you an example. So, a well completed in a confined aquifer is pumped at a rate of 200 cubic meter per day, and the drawdown is measured into two monitoring wells located at distance 10 meters and 25 meters from the pumping well. After a period of pumping, the observed heads in the monitoring wells stabilized with the measured values of 86 meters and 88 meters. What is the aquifer transmissivity? So substitute lang natin sa equation. Transmissivity equals Q over 2 pi divided by H2 minus H1 ln R2 over 1. So Q ang water flow, rate of water flow, which is 200 cubic meter per day. And ang H sub 2 natin, 88 meters, and H sub 1 natin, 86 meters. So, substitute lang natin mga values. We will get 200 cubic meter per day all over 2 pi multiplied by the difference of 88 meters and 66 meters ln 25 meters over 10 meters. We'll get that answer at 15 square meters per day. So, sa unconfined aquifer naman, ang hinahanap natin dito ay ang hydraulic conductivity, K, which is the ease which water can move through an aquifer. Hydraulic conductivity can be determined by dividing the transmissivity of the aquifer by the aquifer thickness. So, the hydraulic conductivity can vary in geological unit over relative short distances, particularly in fractured rock aquifers. So, in this slide, we have here the equation of the hydraulic conductivity. K equals to Q over pi multiplied by B sub 2 squared minus B sub 1 squared ln R2 over R1. So, yung difference ng confined sa unconfined aquifer is if makita nyo sa previous slides, yung depth ng tubig sa confined is fixed or hindi siya nagbabago. Dito sa unconfined, nagbabago yung depth ng or hindi fix yung depth ng water table, yung source ng water. So, pag nagpump ka ng tubig, pag nagpump ka ng tubig, hindi pare-pareho yung area ng yung sa cylindrical or sa well. Hindi pareho yung area. So, habang bumababa yung tubig, the pressure, yung bumababa yung tubig, as you apply pressure, nag-iiba din yung area, meaning hindi na siya completely cylindrical or yung area na nagbabago. So, ganun pa rin dito sa equation, Q over K equals to Q over pi B sub 2 squared minus B sub 1 squared ln R2 over R1. So, yung naalis lang yung 2. So, itong B sub 2 squared minus B sub 1 squared, ito pa rin yung drawdown ng well. And R2 over R1, ito pa rin yung distance. Ito yung distance from the initial height ng well, B2, R2, ito yung initial, yung distance or the static pressure head. Ito yung distance from which nakikita nyo, yung B2 and yung distance niya is R2, distance from the well. And sa B1, ang distance naman niya na from the well is R1. So, ito yung distance or yung static pressure head.
The time interval between recharge and discharge point is defined as the travel time of groundwater flow. A local increase in the hydraulic conductivity leads to a decrease in the travel time. This feature is more commonly observed in saltwater bound lenses. When the hydraulic conductivity is similar, there is a decrease in the travel time as the recharge increases. When considering groundwater travel time, we use the concept of a packet of water, to represent a small amount of water that flows together without splitting up into smaller portions. Sometimes, the term particle of water is used to mean a packet of water. If the groundwater velocity is uniform along a flow path, the time required for a packet of water to move from one location to another along the flow path is computed by dividing the distance of travel by the groundwater velocity. Now, this is the formula that we are going to use to calculate the travel time of groundwater flow. Travel time is equal to d, or the distance between 2 points, over v, or its actual velocity. Travel time is used in several applications such as designing exploitation, monitoring systems, identifying areas affected by contaminant migration, and assessing the potential for natural attenuation of pollutants. The relationship between discharge velocity and seepage velocity. Discharge velocity is the flow velocity out of a cross-section, while seepage velocity is the velocity around soil grains. Now, here is the derivation of the formula for obtaining the actual velocity of a groundwater. Actual velocity is equal to velocity of water over its porosity. Let's have an example. A confined aquifer has a source of recharge as shown in the figure. The hydraulic conductivity of the aquifer is 40 meters per day and its porosity is 0.25. The piezometric head in the two wells 1,200 meters apart is 65 meters and 60 meters respectively from the common data. The average thickness of the aquifer is 25 meters and the average width is 4 kilometers. What is the seepage velocity? Compute the time of travel from the head of the aquifer to a point 3.3 kilometers downstream in days. This is the figure for that problem. First, we are required to find the seepage velocity. Since we are dealing with confined aquifer, we can say that seepage velocity is equal to actual velocity. And we have a formula for actual velocity. Actual velocity is equal to velocity of water over porosity. But according to Darcy's law, velocity of water is also equal to Ki, where K is the hydraulic conductivity and I is the hydraulic gradient. So we have now a new formula for actual velocity. Based on the problem, K, or the hydraulic conductivity, is equal to 40 meters per day, and I is equal to 65 minus 60 all over 1,200, and N is 0.25. So we have now the value of the actual velocity, which is 0.6 meters per day. We can now find its travel time. 3,300 meters over actual velocity 0.6 meters per day. The travel time is equal to 5,500 days.